All right, let's get started. So, hello everyone, this is SeungryongKim. Today we will continue self-supervised referential learning. So last week we introduced what is self-supervised learning and what is the loss function for the contrast learning and few kinds of technique for contrast learning, something like MOCO, SimSiam, or Paro twins, something like that. Right? And today we will start with the paper presentation by Sojin. So the paper title, Exploring the Simple Siamese Separated Learning, just called SimSiam Network. And then we will continue the evaluating supervised learning and supervised learning in vision transformer, right? Okay, so Sojin, okay, please start.
네, hello, I'm Sojin Lee. I present about exploring simple Siamese network representation learning. There are contrastive learning like SimCRL, MOCO, and BIOL. SimCRL is attracting the positive pairs and repulsing the negative pairs. MOCO makes one branch of Siamese networks become a momentum encoder. BIOL relies only on positive pairs, but it does not collapse in case a momentum encoder is used. Let's take a look at the advantages SimSiam bring forward over this method. Siamese networks have become a common structure in various recent models for unsupervised visual representation learning. Typical Siamese networks are characterized by negative sample pairs, Raj matches, and momentum encoders. However, there is an undesired trivial solutions of Siamese networks, where all outputs are collapsing to a constant. SimSiam removed the momentum encoder, negative pairs, and align clustering, which are characteristic of existing Siamese networks, but they achieve comparative performance without collapsing problems. Siamese networks can naturally introduce inductive biases for modeling invariance. Invariance means that two observations of the same concept should produce the same outputs. The weight-sharing Siamese networks can model invariance with respect to more complicated transformations. In this figure, shows the model architecture. Encoder F consists of a backbone network and a projection MLP. First, they apply one image with two augmentation views. Encoder F outputs Z1 and Z2. Second, a prediction MLP H is applied on one side Z1. The output is P1. Next, a stop gradient operation is applied on the other side. The model maximizes the similarity between both sides. SimSiam used neither negative pairs nor a momentum encoder. SimSiam minimizes negative cosine similarity between two output vectors P1 and Z2. Equation 1 uses L2 norm. Equation 2 is a symmetrized loss. This is defined for each image, and the total loss is averaged over all images. Its minimum possible value is -1. Equation 3 is an important component stop gradient operation for this method. It consists of the A and B part. Each part means that Z vectors are considered as a constant. The encoder on X2 receives no gradient from Z2 in the first term A, but it receives gradients from P2 in the second term, and vice versa for X1. This paper pays attention to what may contribute to the non-collapsing solutions. Figure 2 compares with and without stop gradient. Left shows the training loss without Without stop gradient, the optimizer quickly finds a degenerative solution and reaches the minimum possible loss of -1. To show that the degeneration is caused by collapsing, They study the standard deviation of the L2 normalized output. If the outputs collapse to a constant vector, their standard deviation over all samples should be 0 for each channel. This can be observed for the red curve in the figure 2. As a comparison, if the output Z has a 0 mean isotropic Gaussian distribution, it can show that the standard deviation of Z prime is 1 over root D. In the middle picture, the blue line indicates that the outputs do not collapse. In the right graph, shows the validation accuracy of a KNN classifier. These experiments show that there exist collapsing solutions. The collapse can be observed by the minimum possible loss and the constant outputs. Table 2 reports with different batch sizes. SimSham works reasonably well over this wide range of batch size. The results are similarly good when the batch size is from 256 to 2048, and the differences are at the level of random variations. It is one of contributions of SimSham because SimCiral and SWAV both require a large batch for 4096 to work well. A specialized optimizer like Lars is not necessary for preventing collapsing. Table 3 compares the configuration of batch normalization on the MLP heads. In case A, they remove all batch normalization layers in the MLP heads. This variant does not cause collapsing, although the accuracy is low. The low accuracy is likely because of optimization difficulty. In case D, adding batch normalization to the output of the prediction MLP does not work well. It is not about collapsing. The training is unstable and the loss oscillates. In summary, batch norm is helpful for optimization when used appropriately, which is similar to batch norm's behavior in other supervised learning scenarios. Table 4 compares with the state-of-the-art frameworks on ImageNet linear evaluation. Despite SimSham's simplicity, for example, small batch size, neither negative samples nor a momentum encoder, SimSham achieves comparative results. It has the highest accuracy among all methods under 100 epoch pre-training, though its gain of long training is smaller. It has better results than SimCiral in all cases. Table 5 compares the representation quality by transferring them to other tasks, including object detection and instance segmentation. They fine-tune the pre-trained models end-to-end in the target datasets. A common structure is the Shams networks, and Shams networks are generally successful. Thank you for listening my paper presentation.
Right, thank you very much. Question?
네.
No? Okay. So let's move to the code review, right?
네.
코드 있죠? 네.
네, 화면 보이시나요?
네, 보입니다.
네, 심삼 코드는 되게 간단한데요. 일단 데이터 어그멘테이션을 수행해서 두 개의 그 어그멘테이션 된 뷰를 만들어내는 것부터 시작합니다. 그래서 일단 제가 코드를 여기 그 주피터에다 넣어놓긴 했는데 뭐 학습 과정 같은 거는 시간이 되게 오래 걸려서 뭐 인퍼런스 같은 건 따로 넣지 않았고 이 전체적인 심샴을 돌리기 위해서 필요한 그 인풋 데이터 만드는 거 그리고 모델 그리고 학습하기 위한 내용으로 간단하게 구성해 놨습니다. 여기 toCrop transform이라는 클래스에서는 그 이미지를 하나 받았을 때 그거에 대한 트랜스포메이션을 수행하는 걸로 구성되어 있는데요. 여기에는 베이스 트랜스폼이라는 데다가 랜덤 요소가 들어간 트랜스폼을 어그멘테이션 요소를 넣어주면은 같은 이미지에 대해서 이렇게 두 개를 수행하면 이 Q랑 K는 다르게 크롭된 이미지가 나오게 됩니다. 그리고 여기는 가우시안 블러가 있는데요. 가우시안 필터를 적용해가지고 그 이미지에 약간 흐릿한 요소를 추가해주는 그러한 클래스입니다. 이렇게 데이터 어그멘테이션은 이렇게 두 개로 구성되고요. 그 다음에는 이제 모델에 대해서 설명해 드리겠습니다. 이 심샷 모델은 되게 간단한데요. 일단 그 인코더가 하나 있고요. 인코더로 보통 뭐 레지넷 50 같은 거를 설정해주고 이 인코더의 마지막 FC 레이어에다가 그 배치 노멀라이제이션을 추가해주는 걸로 구성이 되어 있는데요. 아까 그 PPT에서 설명해 드렸는데 그 인코더 위에다가 MLP 헤즈를 붙이는데 이 MLP 헤즈에 대한 내용이 그 여기 있는 그 encoder.fc라고 보시면 됩니다. 그래서 인코더 FC 레이어에 배치 노멀라이제이션을 추가한 3레이어 프로젝션을 만들고요. 그 다음에 인코더 D에 붙일 MLP 프레딕터를 선언하게 됩니다. 그래서 제가 아까 페이퍼 프레젠테이션 했을 때 배치 노멀라이제이션을 MLP 헤즈에 넣은 거랑 안 넣은 거에 대해서 그 실험한 그 테이블을 말했었는데요. 그래서 이 부분에서 배치 노멀라이제이션을 넣은 거랑 안 넣은 거 해서 성능이 어떻게 차이가 있다라는 부분이고요. 이 부분을 보실 때 아까 그 테이블을 참고해서 보시면 좋을 것 같아요. 그러고 나서 이제 포워드를 수행하는데요. 되게 간단합니다. 일단 그 X1, X2가 같은 이미지에 대해서 어그멘테이션한 서로 다른 뷰를 가진 그런 이미지가 되고요. 그래서 X1이랑 X2를 동일하게 인코더랑 프레딕터를 거쳐서 P1, P2를 얻어냅니다. 근데 여기서 그 Z1이랑 Z2는 디태치를 해서 그레디언트를 분류하는데요. 이게 그 로스 식에서 마이너스 코사인 시밀러리티를 구할 때 한쪽에만 그레디언트가 흐르고 다른 쪽에는 안 흐르게끔 양쪽을 번갈아 가면서 하는 부분이 있어요. 그래서 이렇게 아웃풋을 포워드에서 내보낼 때 그레디언트 흐르는 부분이랑 안 흐르는 부분 해가지고 나눠서 내보내게 됩니다. 그러고 이제 그 프리트레이닝을 위한 아규먼트를 설정하고 이제 메인 문으로 들어왔는데요. 보통 그 심산이나 다른 그 컨트래스티브 러닝 같은 거 보면은 디스트리뷰티드 데이터 패러렐로 설계가 되어 있는데요. 이게 보통 배치 사이즈가 되게 크게 형성되어 있기 때문에 DDP로 구현되어 있고요. 네, 여기는 다 DDP에 대한 내용이고 이제 unsupervised pre-training에 대한 내용입니다. 일단 GPU 뭐 DDP를 설정할 건지에 대한 GPU 설정을 다 해주고 나서 그 다음에 모델을 만들어 준 다음에 수행을 하게 되는데 그 코드에 뭐 DDP 설정에 관한 내용이 되게 많습니다. 그리고 제가 여기에 넣어놓은 코드는 그 페이스북 리서치 예전에 페이스북이었죠. 네, 거기에서 그 공식 코드에서 가져온 거여가지고 DDP 8개로 하는 그런 방식만 들어있습니다. 그래서 혹시 싱글 GPU로 실험해보고 싶으신 분들은 다른 코드를 한번 참고해 보셔도 좋을 것 같습니다. 이제 모델을 다 선언하고 난 다음에 이제 코사인 시밀러리티를 선언을 하게 됩니다. 그래서 코사인 시밀러리티를 사용하겠다라고 하고 이제 옵티마이저를 설정하게 됩니다. 일단 여기는 옵티마이저는 보통 SGD를 썼고요. 라스는 이제 특수한 케이스에서도 따로 설정하실 수 있는데 보통은 SGD로 논문에서 진행하고 있습니다. 그래서 여기서 트랜스폼 하나의 이미지에 적용할 어그멘테이션을 위해 트랜스폼을 설정해 줬는데요. 이 트랜스폼 요소에 반드시 랜덤 크롭이랑 그리고 다른 랜덤 요소가 들어가야 이 어그멘테이션을 하나의 이미지에 2번 적용했을 때 다른 그 패치 부분이 나오게 됩니다. 이렇게 어그멘테이션을 설정하고 이걸로 트레인 데이터를 만들게 됩니다. 그래서 로더를 넣고 이제 트레인을 시작하게 됩니다. 그래서 마지막으로 이제 트레인 함수를 보게 되면요. 네, 로더에서 불러와가지고 네, 이미지를 하나씩 넣게 됩니다. 이미지를 하나 넣어서 아까 그 심샴의 포워드 부분에서 그 인코더랑 프레딕션을 다 한 P1과 P2랑 인코더만 거쳐서 그레디언트를 디테치한 Z1, Z2가 있었죠. 이렇게 P1, P2, Z1, Z2를 얻어낸 다음에 이걸 통해서 여기 네거티브 코사인 시밀러리티를 적용한 로스 펑션을 수행하게 됩니다. 그래서 그 로스 펑션에서 이게 절반, 그 왼쪽 절반이랑 오른쪽 절반이 있는데 여기에서는 P1, Z2 그리고 오른쪽에서는 P2, Z1으로 그 브랜치가 왼쪽 브랜치, 오른쪽 브랜치 2개가 있을 때 한쪽 브랜치에만 그레디언트가 흐르는 걸로 결과를 구하고 또 나머지 브랜치에만 그레디언트 흐르는 걸로 결과를 구해서 이 결과를 합친 다음에 이거를 수행하게 됩니다. 그렇게 로스를 만들어서 이제 그레디언트를 흐르게 해서 이제 학습을 진행하고요. 이제 밑에는 그 리니어 클래시피케이션 내용인데요. 그 프리트레이닝 했던 과정이랑 거의 유사하기 때문에 이건 그냥 한번 보시면 그냥 될 것 같습니다. 네, 내용은 비슷합니다. 네, 여기까지 했는데 혹시 질문 있으신가요?
네, 아이고 깔끔하게 정리 잘해줘서 고맙고요. 혹시 질문 있으신 분들? 전? No? Okay, thank you very much. And
네, 감사합니다.
네, okay, let's move to the main lecture. Okay. Right. Yeah. So far, we discussed the self-supervised left-hand learning in the image level, right? So we discussed the SimSiam, BYOL, or Moco, something like this, and Sojen introduced the SimSiam in detail, right? And we will, from now on, we will talk about how to evaluate your self-supervised left-hand learning method, right? Self-supervised left-hand learning method have been proposed in so many papers, but comparing to the supervised learning technique, we don't have any supervision, right? It means that we can't use any previous evaluation taxonomy to evaluate your self-supervised learner. So we need meta task or the meta metric to evaluate your self-supervised representation learner. So there are several kinds of way to evaluate your self-supervised learning method. So first of all, most important and the simplest one is linear classification. Given an image X, we can use the pre-trained model from the self-supervised learning technique, and then we can fix this one, right? And from the output of input image X, let's say this is Z, and we can use additional linear layer, for example, MLP module, to classify these images. This linear module, I mean the dimension of the final output, it depends on what kinds of data set you want to evaluate. For example, ImageNet, Place 205 or Pascal VOC or COCO can be used to evaluate your self-supervised learner. So this is the examples of a linear classification. When we fix the backbone model and just to train a linear classifier here, well-trained letter in a self-supervised learning method can achieve the even better performance compared to the supervised learning method, right? Purpose on this benchmark, in this case, ImageNet benchmark, has accelerated strongly in the past year, closing the gap with respect to the supervised learning. In this case, Sinclair, but after that, there were so many kinds of this one, right? And this is the first method. The second method is the fusion learning. Fusion learning. So the question is, what is a good representation? What is good representation? The low, the small loss cannot guarantee good representation, right? So good representation should be well transferred to the other task or the unseen domain or unseen task. In other words, good representation should have good generalized performance, right? Fusion learning technique, the fusion learning problem is one of them. To achieve the good fusion learning method, our network should be shouldn't to over PT to the training data, because the fusion in fusion learning framework we build the disjoint training and testing data with the different class label, right? Class label set, right? So good fusion learner have to learn, learn to measure the relationship between the separate and core images, right? And it should be transferred to the unseen class label, right? So in this kind of technique, good feature representation is one of the most important key ingredients to accelerate the fusion learning technique. So when you develop the good self-fusion learning method and train your network with your self-fusion learning technique, we just transfer your pre-trained model to the fusion learning technique, which is one of the most popular technique to evaluate your self-fusion learner. So in this kind of technique, the self-supervision reaches to relatively competitive performance against the supervised cosine classifier here. So please check the paper. Another task, another evaluation task is efficient classification. Efficient classification means, okay, comparing to the linear classification, we do not use whole the label data, but we only use subset of the label. For example, 1% or the 5% or 10%, then train your model to evaluate on the validation step. It means that with such kinds of small data, the network, if network have the good generalized performance, it can be well transferred to this kind of efficient classification problem. So the structure is like that. We use the pre-trained model here, but in this case, we will fine-tune because this task is very challenging, right? And we also use the linear classifier here, maybe MLP, and just train with a small scale labeled data. For example, on the ImageNet or the VTAB, something like this, and evaluate. Here's like that. So when we set the label fraction as a 1% or the 10%, supervised baseline can achieve the relatively full result. Why? Right? Because lack of the supervision, right? But in self-supervised learning case, because it already learned the good representation, for example, like the low-level picture or the high-level picture, it can achieve the good performance even with just the 1% label data as a 85% on ImageNet classification task. So yeah, this is the efficient classification method. Another method is the transfer learning, especially object detection or the semantic segmentation. As we discussed in object detection and semantic segmentation, we just fine-tune, we just use the backbone model and set the following, the task-specific module. For example, in semantic segmentation task, we use the decoder or the generator, something like this, and then just fine tune this one again and measure the performance. Object detection or semantic segmentation or surface normal and visual navigation is the popularly used data set or the task. Here's the example, right? And supervise the means the backbone model, in this case less than 50. Backbone model start from the image net pre-trained model, and comparing to this, the mock pre-trained model outperforms the supervised learning backbone as a starting point. So yeah, it shows that self-supervised learning have the better generalized performance for in this case in task prediction case. I mean, all right. So in supervised learning case, they also use the ImageNet classification label, right? But in image, I mean the object detection, we require not only image level good feature vector, but also good intermediate feature vector, because we need the feature vector that preserve the spatial resolution, right? Then intermediate feature vector should be better compared to the supervised learning method, right? In this case, the self-supervised learning method does not have any constraint, so it guarantees the better performance, right? So natural question is, the next natural question is, can we improve self-supervised learning by using vision transformer? Maybe yes, right? So nowadays we lived in vision transform world, so maybe the know-how from the self-supervised learning technique can be directly used to train your vision transformer. There was so many kinds of paper for this kind of task. First one is SIT, self-supervised vision transformer, SIT, right? In this paper, they just use I mean the know-how from the NLP and vision simultaneously. So let's go back to the self-supervised learning in NLP field. They just use the masking technique to improve the context awareness of the network, right? So it was the know-how from the NLP, and in know-how from the computer vision, there was the rotation estimation or the contrast learning, stuff like this, right? And in this paper, for the single vision transformer, they just want to use several kinds of self-supervised learner that I mentioned previously, which is from the vision. Let's say which is from the NLP. In fact, it's not true, but let's just say that NLP, because the masking technique initiated from the NLP field, it's not first attempt, but BERT or the transformer, maybe the first attempt to successfully use this masking technique, right? Anyway, so given an original image, they first apply the augmentation or the collapsing. For example, like this one or this one, noise or the cut mix or something like this. And then they just to patchify the input images and linear projection of the flat features and feed to the vision transformer. And then on the features from the vision transformer, we can use the linear projection network again to transfer, I mean, to embed feature vector to the image space, something like this. Good feature representation, I mean, the feature representator here should well reconstruct the original image, looks like this. So they just give reconstruction loss between the reconstructed image patches and the original patches. In addition, they use two additional pretext. For example, similar to the vision task, they just apply the rotation on original image, and this additional rotation head estimate the rotation applied to the original images, right? Which also very, very similar to the previous vision task, right? And they also use the contrast learning here, similar to the Moko, SimSiam, or other technique. They apply two different image level augmentation and make a two view and extract the feature vector from the P1 and P2 simultaneously and minimize use contrast learning. Of course, for this output, we need additional token for the rotation and contrast learning, and then we can just train whole the transformer with these three kinds of loss function. It was the SIT, self-referential vision transformer. And they also investigate what kinds of augmentation is useful to train vision transformer. For example, random crop or random replace, which is highly similar to the comp mix, right? And color distortion, blurring, or the grayscaling. In this case, locally grayscaling, something like this. And they discuss what kinds of augmentation can be used. If you're interested, please read this paper. And similar to this idea, there was the very, very important paper, Dino, self-distillation with no label. In fact, it's not a self-supervised learner, but it's a self-distillation paper. Okay, by the way, the question, what is the difference between self-supervised learning and distillation technique? Anyone? 자, 갑자기 이거 설명하다 보니까 여러분들 제가 이게 이제 어드밴스 코스다 보니까 막 그냥 넘어가는데, 자, 디스틸레이션과 셉션 러닝 테크닉의 차이를 아는 사람? No? 누가 할까요? 잘 아시는 친구? Distillation versus self-supervised learning. I mean the modern self-supervised learning technique. No? Okay. In a high level, it's almost similar, but it's slightly different. Right. So from the image, maybe this. Thank you. Self-distillation needs to have the teacher model. Negative pair 사용 여부. But if you remember the SimSiam or the BIOL, it's not necessary need negative pair, right? So the main difference is level, where you can apply your loss function, right? So let's suppose that you have two images, maybe these two images from the two views or the same images or the other images. Anyway, you have a backbone model, and you can achieve the feature vector. It might be image level feature vector or the intermediate feature vector. And okay, let's say this is a backbone, and you need another maybe you have a classifier to generate the final class probability or the or your own output. In a high level, self-referential learning works here on the feature level, but distillation technique works in output level. For example, logic level or the probability level. So let me show here. So this figure highly similar to the SimSiam or the SWAV or the BYOL, but the output of this one, it's not a feature vector anymore. It's going to be the logic. Logic means values for each class label. In this case, because this is an image classification task, and with softmax probability and the softmax function, it's going to be the probability P1 and P2. Okay, and in this paper, they build the teacher network with the EMA, which is exactly the same with MOCO, right? But main difference are here. So loss is defined on the probability level, but they use a similar technique centering from the SWAV, just the normalization, and subgradient from the MOCO for the PY1. And by minimizing this loss function, this is the cross entropy loss, because this is image classification and just vector park here. Interestingly, this simple kind of technique is designed for the distillation, but it interestingly works very well for the self-distillation technique. So it gives the very important message to the society. Anyway, they just compare. I mean, the Dino paper compare their method with the other technique. In fact, it's not compare. It's not fair, because they are just designed for the the feature level loss. It's unfair, but they just compare with this one and shows the better performance compared to the self-supervised learning technique. And this is the examples of the self-attention from the vision transform trained by Dino self-supervised distillation with no label. So without any supervised learning technique, it shows that highly compatible self-attention has been trained, for example, here or here, without any image class supervision. In another paper, empirical study of the training self-supervised vision transformer, they just compare self-supervised learning framework on vision transformer. Okay, so far, most of the self-supervised learning paper just use a convolutional neural network, for example, LessNet 15, right? But in this paper, they use similar self-supervised learning technique. But we did not discuss the MOCO V3, but it's highly similar to the original MOCO with some variant. So if you're interested, please check the paper. Anyway, they apply this MOCO framework to the vision transformer, VIT based, VIT large, or VIT hybrid, something like this, blah blah blah. And interestingly, as increasing the number of parameters in vision transformer, we can achieve the better performance even with same self-supervised learner. This is very, very interesting and important observation. In previous self-supervised learning papers, even though we use the good self-supervised learner, if we increase the number of parameters in CNN, the performance boost was not so meaningful, because the capacity or the CNN or the maybe due to the inductive bias of the CNN, but when we use the vision transformer as increasing the number of parameters as much as you can, we can achieve the better performance. This is very, very important method. And after that, I mean, at the end of today's lecture, we will talk about the CLIN model, which is one of the biggest network, and they can achieve very impressive performance on most of the computer vision tasks we'll discuss later. Anyway, like this. In another paper, BEIT, BERT pre-train of the image transformer, BEIT. In this paper, they just try to resemble BERT training in NLP field. But comparing to the NLP image feature vector, I mean the image pixel or the image feature vector does not have any tokenization technique, right? Compared to the NLP field, where the word token, the word dictionary is used to define your word level or word feature vector. So in PEIT, they just use tokenizer to make a visual token. How can you do that? This is very, very well-known technique to tokenize your visual feature vector on the embedding space. And then to train this visual tokenizer, they use the decoder to reconstruct image. So this is kind of autoencoder, but they can train visual token here. And then in transformer encoder training procedure, they just use here and they just follow the vision transformer training. First of all, patchopize images and masking, block-wise masking here, and flattening and feed forward through the encoder, VIT encoder in this case, and estimate the masked feature vector for the each mask region here and here, and with one additional head, and estimate the visual token and compare to the consistency between the original visual token and estimated visual token. So this is kind of consistency loss, but by using this kind of technique, we can train a vision transformer similar to the masking technique in BERT model. So this is a PEIT. We have a paper stunt paper presentation for the PEIT today. Let's see later. Any question? 자, 여기까지 너무 그냥 명확한 얘기들이라 그냥 쭉쭉쭉 넘어오고 있어요. 그렇죠? 그래서 한 번만 더 설명할까요, 한국말로? 비전 트랜스포머 오기 전에 비전 트랜스포머가 2021년도 후반기부터 이제 비전 쪽 이렇게 활발하게 사용되기 전부터 사실 셉션 러닝 기법들, 심시함, 오늘 봤었던 심시함부터 BYOL 쭉쭉쭉 학습이 되고 있었죠. 연구가 되고 있었고 지금도 되고 있어요. 정말 많이 연구가 되고 있는데 당연히 비전 트랜스포머에 적용을 해볼 수 있겠죠. 그래서 이제 이런 태스크에서는 비전 트랜스포머의 어떤 멀티플 프리텍스트들, 로테이션 에스티메이션, 컨트라스트 러닝, 앤 마스킹, 그러니까 결국 이 뭐예요? 컬럽싱을 넣는 게 마스킹 효과가 있으니 결국 마스킹 효과와 비슷하게 이렇게 리컨스트럭션 로스를 줘서 학습하는 연구도 있었고요. 그다음에 결국에 제가 디스틸레이션이라고 표현했는데 엄밀하게 하면 이거는 셀프 슈퍼바이즈드 레퍼런트 러닝은 아니고 셀프 슈퍼바이즈드 러닝 for the image classification이죠. 그렇죠? 그러니까 결국에 이게 바로 아까 디스틸레이션이랑도 연관이 되는 거고 이런 프로버티 레벨에서 로스를 주지만 정말 재밌는 건 그 테크닉들이 이 뭐예요? 셀프 슈퍼바이즈드 레퍼런트 러닝에 썼던 테크닉들이 정말 유사하게 쓰였음에도 불구하고 성능이 잘 나오더라. 그 말은 뭐냐? 이 당시까지만 해도 셀프 슈퍼바이즈드 레퍼런트 러닝에 연구되었던 어떤 테크닉들과 디스틸레이션 또는 컨셉션 레귤라이제이션과 같은 테크닉들이 어떤 별개의 태스크로 연구가 되어 왔지만 그래서 그 각각의 어떤 태스크마다 다른 진리의 파편들을 찾아왔지만 실제 이제 그것들을 보다 보니까 많은 것들이 비슷하더라. 또는 그 다른 테크닉에 쓰였던 테크닉들이 많이 쓰일 수가 있더라 라는 거죠. EMA 디스틸레이션 썼었고 셀프 슈퍼바이즈드 러닝에 썼었는데 결국에 둘 다 좋은 성능을 냈었던 거죠. 그렇죠? 이런 것들이었고요. 다이노란 페이퍼였고 그다음에 이제 비전 트랜스포머를 이제는 셀프 슈퍼바이즈드 러닝을 해봤을 때 어떤 특성들이 있나 이제 메시지를 찾아보려고 했던 시도에서 ICCV 2021년도에 나왔던 논문 같은 경우는 셀프 슈퍼바이즈드 러닝 프레임워크를 모코 V3로 고정시켜 놓고 이 VIT의 어떤 러너 파라미터 수를 늘리면 늘릴수록 성능이 좋아지더라 라는 어떤 매우 중요한 옵저베이션을 발견해냈고 이제 많은 메시지를 준 거죠. 결국에 비전에서 트랜스포머를 써야 되나 말아야 되나의 논쟁이 더 이상 의미가 없어지는, 그쵸? 파라미터가 많아질 거고 우리의 GPU는 더 좋아질 거니 무조건 써야 된다라는 결론에 도달하게 된 거죠. 그렇죠? 물론 이 논문 말고도 그 전에 많은 논문도 나오긴 했지만 그러면서 이제 또 비슷한 시기에 ICCV 이제 BIT라고 해가지고 버트 프리트레이닝을 바로 이미지로 바꿔보려는 시도가 있었는데 가장 중요했던 게 이미지의 결국에 이미지 픽셀들의 또는 이미지 패치들 또는 이미지 피처들은 토커나이제이션이 안 된다라고 하는 거예요. 그렇죠? 어떤 워드들은 토큰으로 나눠질 수 있기 때문에 쉽게 학습이 되지만 토크나이제이션 안 되는 상황에서 이런 컨시스턴 레귤라이제이션으로 동작하는 마스킹 기법은 사실 동작을 잘 안 하더라라고 하는 게 연구의 아이디어였고, 이러한 토크나이제이션 이제 이게 뭐 많은 텍스트가 많이 쓰이고 있죠. 뭐 예전에 오픈 AI에서 만들었던 뭐예요? 예전 초창기 모델 그 텍스트 투 이미지 만들어냈던, 갑자기 기억이 안 나네. 네, 그 모델부터 해가지고 이제 이렇게 토크나이저, 맞아요, 맞아요, 달리에서도 이제 이런 기법들을 많이 썼었고, 이제 VQVA처럼 이제 토크나이제이션을 써가지고 어떤 이미지를 어떤 토큰 레벨로 인베딩 시키려고 하는 노력들이 많이 나왔죠. 결국에 목표는 다 하나예요. 비전에서 가지고 있는 이미지의 앰비규어티, infinitely many 솔루션을 infinitely many 케이스를 가질 수 있는 어떤 앰비규어티를 줄일 수 있다라는 거였고, 그렇기 때문에 이러한 학습 과정에서 이제 토큰 레벨로 학습이 되게 하면 더 잘 되지 않을까라는 논문이 여기 나왔었죠. Question so far. 자, 네, 여기까지 혹시 질문? 괜찮죠? And there was the error. It's not a PEIT. This is the masked autoencoder paper by Kai-Min He in ICCB 2021. 이거 아닌데? 이거 아니요. CBPR this year, right? 이거 아는 사람, 이거 올해 거죠, 이거? 올해 논문. 마스크드 오토엔코더. 그렇죠? Right? So, masked autoencoder are very similar to the previous work, previous the context encoder. But the main idea is that, right, so we can apply the masking on the input image similar to the previous work, but rather than using holder token, visible and invisible token, in this paper, they propose to use only visible token to train the encoder and extract the visible feature vector. And then in decoder part, they decode holder token with very shallow decoder and make a consistency loss between the input and target image. And actually, in fact, it's not a masked input, original input. So, like this. So, comparing to the previous work here, if we erase a number of token in VIT here, if we use holder token here, there might be so many redundancy because the mask token does not have any information. So using this kind of visible token, we can highly boost the training time with the lower complexity to compute the encoder part, and then we can reduce the complexity in the decoder part with a smaller transformer. Then we can accelerate training in a masked autoencoder case. So this is the interesting idea. Interestingly, comparing to the previous method, they dramatically mask some region. This is the original. This is a masked input where masking ratio was about 80%, leaving only 39 out of the 196 patches like this. Surprisingly, with this kind of very small number of patches, this masked encoder rarely construct looks like this. And after that, we just remove the decoder part and just use the encoder part, which can be transferred to the downstream task. This is masked autoencoder. Yeah, this. And they compare their masked encoder, which is called MAE, compared to the PEIT, MOCO V3, or Dino, and they achieved a better performance with the same network architecture. VIT based large hybrids. This is masked encoder, masked encoder. And there's another paper, SIM-MIM, masked image modeling. In this paper, this is also very similar to the MAE, but in this paper, they just use holder token, I mean the mask token, visible token and invisible token simultaneously, but they just show by using one layer prediction hat to estimate the image for the invisible token and just use error norm between the original patches, like this. We can train the good visual encoder, vision encoder, for example, VIT, swing transformer, or something like this. This is called the SIM-MIM and masked image modeling. Yeah, and in this paper, they show different masking strategy for mask your images, for example, scale, black white, random, with a different window size, something like this. And they exhaustively conduct so many experiments with this kind of mask type. This is kind of the different augmentation, right? So the performance was relatively, the performance gap was relatively small, but in some rate, with the mask patch size is 32, with the mask ratio 0.5, we can achieve the good representation here. So this is very, very important message. If we can find out good, if we can find out what to say, the search algorithm to optimize mask patch size or the mask ratio given your data set, it's very important paper. It's going to be very important paper. Why? Training vision transformer with one single stage, one single setup. Look here or here, like will be very, very challenging, right? Because the time complexity. So this is the kind of very interesting direction. Anyway, this is the end of image level reference learning. Any question? 자, 그래서 이제 이렇게 해서 물론 엄청나게 많은 페이퍼들이 있죠. 이거 말고도 많이 나오고 있는데 이런 연구들이 진행되고 있더라. 그래서 결국에 비전 트랜스폼까지 오면서 이제 이러한 셀프 슈퍼 레퍼런스 러닝은 마스킹에 대한 고민들로 접어들었더라 라고 이제는 결론을 낼 수가 있게 되고, 이 논문까지 결국에 어떤 마스킹을 쓰느냐에 따라 사실 성능에 엄청난 차이가 있지 않지만 나름 의미 있는 차이들은 보여요. 그렇죠? 결국에 어떤 마스킹을 쓰는 게 최적일까가 향후에 조금 연구가 더 나올 것 같고요. 아마 이런 마스킹 기법이 가장 옵티멀한 솔루션이 아닐까라고 어느 정도 단정은 지어봐요. 왜냐하면은 결국에 NLP에서의 마스킹과 트랜스포머의 조합이 아직까지도 가장 소타이였던 걸 보면 비전에서도 비슷한 경향을 따라가지 않을까 싶기는 합니다. 오케이? question. Right. Okay, this is the end of image level apparent learning, and then from now on we will move to the pixel level apparent learning. Time 2:54. Right. So before that, let's take a 6-minute break and let me start in 3 p.m. 우리 6분만 쉬었다가 3시에 다시 시작합시다. Right, let's continue. Let's continue. Because we have three student presentation today. So I think I have to finish within 30 minutes, maybe. Yeah. Okay. So far we discussed self-supervised reference learning per image level presentation. For example, we have an input image and our model generate the image level picture vector, which maybe this is going to be one by, for example, 1024, something like this. This kind of technique can be applied to the image level task, for example, image classification or the image retrieval, something like this. But this one, intermediate feature vector, can be transferred to the object detection or the semantic segmentation as well. But in many cases, we require the pixel level representation. For example, like this. Output of our network should preserve the spatial resolution. So we need a spatially varying feature vector. Many applications require such kinds of the intermediate representation or pixel representation or dense representation. For example, image matching, object detection, semantic segmentation, or depth estimation, or something like this. So how to directly train pixel level representation in a self-supervised manner is limited studied. So I think the next direction, one of the next direction for the self-supervised reference learning is going to be the dense representation. The question is similar to the image level, how to collect good positive and good negative sample for pixel level representation. So let's go back to the image level representation. For example, right, we have a XQ and XK, two view images, backbone and global projection module, and we extract the Q and K. This is global picture vector. Then we can apply the contrast loss here. But pixel representation, we extract the from the same images, we extract the picture vector that preserve the spatial resolution. Looks like this. Let's say this is a 3x3 by 1024. In this case, just 1024, 1 by 1 by. Then we can apply the dense construct loss similar to the image level representation, but problems are here. In this case, we don't know positive samples here. Why? Okay, in image level representation, there is no we don't need any kind of the alignment, pixel level alignment, because even though we use the different spatially different images, but we need to extract the same image level picture vector. But in pixel level representation, if these two images does not have the same structural alignment, then we cannot set same spatial position as a positive value, and negative samples are here, remaining part. So the main research direction is how to find out good positive, although we require the good negative sampling, but how to find out good positive sample. In other words, how to establish correspondences between the two views. This is the research topics in the pixel level representation. In first paper, dense CL, dense construct learning for the self-supervised visual pre-training model, they use winner take all to make a positive sample, to find out positive sample. The strategy is like that, right? So here is a 3x3 and 3x3 case. Then if we compute the similar each other, we can make 9x9 score map. 그렇죠? 9x9 score map. And for each vector here, let's say here, if we search the most similar patches on the another images, maybe here, or for this one, maybe here, something like this, we can set this one as a positive, while remaining part are negative. So this is kind of winner take all defined such that similarly between Fi and Fj, Fi are here, Fj are here. So argmax, finding argmax in terms of J, which is going to be the correspondence for the pixel ith entry. So let's say this is Ci. This is examples of the correspondences during training. Then use this one as a positive and use the dense contrast learning loss function. In another paper, VADER, on by learning of the dense visual representation in URIS 2020, they just use synthetic positive sample. For example, if we have images, we crop the two view, looks like this and looks like this, and we already know this one is positive, and this one is exactly the same, so it's going to be positive, or this one also should be positive. Then we extract a picture vector and make these two picture vector similar, while other images, other picture vector from the other images should be negative. So similarly between this one and this one should be dissimilar. This is very simple method, view agnostic dense representation, but it has a critical limitation. This part and this part does not have any positive sample, so it's going to be redundant, right? So it may be suboptimal, but anyway, when we apply the VADER to the downstream task that require the pixel representation, for example, segmentation, semantic segmentation, depth estimation, or the video instant segmentation, VADER provide the good initial point. I mean the good initial parameter for the backbone network, pixel backbone network. There was another paper called the Pixpro. They used a similar technique to the VADER. From the single images, they extract the two view 1 and view 2, and use the backbone and projection with the momentum here, and extract the picture vector x and x prime. But here, x and x prime is not an image level picture, pixel level picture vector. And we already know these two values should be consistent, so we can use the pixel level contrast loss similar to the previous method. But one more thing is that they use the pixel to propagation module, PPM module. This is the another contribution. But idea is very simple, right? Idea is very simple. Here, okay, so pixel to propagation here. So we already know they are not exactly the same, right? Because they are quantization error. Why? Because even though it's called the pixel level, they have a lower spatial resolution, right? So it means that it has tried on the original image level, so they are not precisely consistent, right? So by using the pixel to propagation, they want to reduce the gap, this gap, and make a new positive sample y, and define the Pixpro loss, which is called L Pixpro between the y and x prime here. This is Pixpro. And comparing to the image level representation learning method, more simpler, more version 2, or InfoMe, we did not discuss this one, but Pixpro method achieved a better performance on the dense prediction task. For example, object detection, object detection, 이것도 object detection, and maybe this is segmentation. I'm not sure, please check that. Anyway, so for the dense prediction task, this dense representation achieved the better performance. All right, this is just briefly brief overview. And I would like to finish self-supervised referential learning chapter, the lecture, with a clip paper. I guess most of you already know well about clip. The starting point of the clip was similar to the previous self-supervised referential learning. Concept, the typical vision data set is labor intensive to create the images or create the label, right? For example, Imagine required the 25,000 workers to build the image data set, right? Teaching only a narrow set of the visual concept. I told you this is the kind of bias from the image or the image set or the label or the annotator, right? And the idea of the clip is that let's train the network on wide variety of the images with a natural language supervision collected from the internet. So, okay, if you imagine the internet sources, most of the researches have both image and natural language as a supervision, natural language as a parent data. Then we can easily collect image and natural language supervision, even though they have the noise. Then we can use that kind of paired data, pseudo-paired data, to train your model. By not directly optimizing for the data set, the model become more representation, which enables the zero shot. I will show you this one later. So, okay, the clip trained model have the good generalized performance comparing to the previous method because they train the infinitely many images with the corresponding natural language, which is the richer source compared to the just image level class annotation. So we can achieve the better performance, better generalization, and which enables the zero shot image classification. I will show you later. This without fine-tune, clip achieves a competitive leader in various data set, even though without any fine-tune, comparing to the previous self-supervised referential learning techniques, right? Then, what is a clip? So clip is very, very simple. Use image text pair abundantly available across the internet. Given an image, predict which out of set of the 3 to 7, 6, 8 randomly sample the text will actually paired within each data set. So this kind of statement exactly same to contrastive learning or the contrastive pre-training. So here's that. Let's say in one batch we have 4 kinds of paired data, image and text pair, and we can extract the image feature vector here with a CNN or the vision transformer, and we can extract the text feature vector through the, let's say, BERT and T1, T2, T3, blah, blah, blah. Then we can make a similarity map between text features and image features and generate a score map. Apparently, this one, diagonal term, should be 1 if the ideal case, while off-diagonal term should be 0. Then we can formulate this one as a contrastive learning, contrastive loss function, especially, for example, impression loss, right? Similar to the seems clear. With this kind of simple pre-training model, pre-training framework, highly complex or the well-distributed feature vector has been learned, and because it has a good representation, it can be applied to the zero-shot prediction. Idea is very, very simple. Okay, let's say we have images and we want to classify among the class label candidate. and their strategy is like that. We have a prompt. Let's say prompt. This is a text prompt. Then make a, let's say there are k kinds of one, and we can generate the k kinds of feature vector with the text prompt here, and measure the similarity between the image feature vector and text feature vector, and just pick the best one, most similar one. And in this case, if this token is the most similar one, and we can say that this image is the dog class. In this scenario, we did not use any kind of the fine-tune or the additional training, but with a pre-trained image encoder and text decoder, we can do that, right? This is a zero-shot prediction in clean model. You can see here, even though with a clean model, we did not access the previously the data from the Caltech or the Sun or SaiPa, something like this. The good clean model achieved the better zero-shot image classification. Looks like this. Okay. Interestingly, they also proposed the prompt learning. The prompt engineering. So in previous, in original paper, they just use the template as a photo of blah blah blah, right? But they also investigate what kinds of template can be good, can generate the good text prompt. So they discuss a photo or the type of or satellite photo, or use the several kinds of the augmentation on the template and ensemble, which improved the 3.5% on ImageNet classification. Anyway, they also proposed the prompt engineering technique in CLIP original paper. And after that, so many kinds of vision tasks try to benefit from this clean model. One of the benefits is that we can give language level controllability on our vision task, because this clean model transform vision image and text feature to the common embedding space here. So there are so many kinds of paper try to use this clean model. For example, if we go back to our generative model lecture, there was a style clip to manipulate your images with the text text guidance, right? And there were so many kinds of paper. That's it. So yeah, this is end of self-supervised lateral learning, my lecture. In fact, as Jungin said, CLIP is not a SSL because they use pseudo ground truth from here, pseudo image and text pair. But in this scenario, we did not require, we did not use any human supervision, right? So in a high level, we can say that CLIP is one of the self-supervised learning technique or the framework, and CLIP model shows the most the extremely better performance comparing to the previous self-supervised learning technique like the Moku, SimSiam, Power of Twin, something like this. So I think this CLIP paper gives a very, very important message to the computer vision society. So let's see what happened after a few years. Okay. All right. So that's it. So this is the end of the self-supervised lateral learning lectures. Question. Question? No? Right. Then let's move to the stunt presentation. So the first paper is masked autoencoder, scalable vision learner by Jie. So which is going to be paper and code review. Okay, please start.
혹시 화면 보이시나요?
네, 보입니다.
네. Okay, let's start. Hello, I'm Jie Park in Computer Vision Lab, and the paper that I review is Masked Autoencoder, which is accepted in CBPR 2022. Actually, in NLP, there have been many self-supervised methods using mask, like BERT, and the idea of using a general denoising autoencoder has been proposed in computer vision. However, the information density of language and vision is very different, so it was not efficient to apply masking autoencoder or NLP directly in vision task. Therefore, this paper proposed very simple, efficient, and scalable self-supervised learning model in vision. There are two most important things in this paper. The first is that unlike other autoencoders in general, this model has an asymmetric encoder-decoder architecture. Second is that the encoder only takes unmasked patches as input and the decoder receives all patches as input. When the pre-trained masked autoencoder was fine-tuned, it records the 87% of accuracy, which is higher than general VIT. In addition, it shows high performance when transferring to downstream tasks such as object detection and segmentation. Now let's explain the architectures of masked autoencoder in detail. First of all, it divides the image into regular non-overlapping patches by using patchify on VIT. After that, it randomly separates to sample a part of the patches and mask the remaining ones. This process is called random sampling in this paper, and the patches are sampled following a uniform distribution. They apply masking the 75% of patches. By utilizing this high masking ratio, it has the effective of removing redundancy. The encoder uses the VIT structure, and it operates on masked visible patches as input. Since it takes only a few patches as input, very large encoder model can be trained with only little memory and little computational power. Finally, the decoder uses both visible patches learned from the encoder and masked patches not used by the encoder. It also injects their location information by adding positional encoding to all patches before entering the decoder. The decoder is only used for image reconstruction tasks, not for fine-tuning or transfer learning. Therefore, it is independent of the encoder and can be designed flexibly. Therefore, in this paper, they use lightweight decoders, which is narrower and shallower than the encoder were used. The model reduced pre-training time while maintaining good performance. Finally, it only uses MSE loss between the reconstructed image and the original image. At this point, the loss is only applied to the masked patch. Finally, it is said that the representation quality can be improved by applying normalization to the masked patches. As such, the masked autoencoder shows very good performance even though it has a very simple structure. Okay. They experiment various evaluation studies. First, they test how many patches to the mask, and when the masking ratio is 75%, they showed high performance in both linear probing and fine-tuning. For linear probing, the accuracy increases steadily, and the accuracy gap is up to 20%. For fine-tuning, the results are less sensitive to the ratios, and a wide range of masking ratio work well. And blue-white sampling tends to remove large blocks. In 50% of mask ratio, this sampling shows reasonable results, but this sampling suffered performance degradation at 75%, and the resulting image was also blurry. And grid-wide sampling is the method that regularly keeps one of every 4 patches. It is much easier and the training loss is lower than random sampling. However, the representation quality is low. Surprisingly, unlike other self-supervised methods, masked autoencoder shows high performance without data augmentation. This is because random sampling has a rule similar to data augmentation. Because the mask is different for each iteration, the model can produce a different image each time without data augmentation. And there are the comparable results to the other supervised models and the result of transfer learning to downstream task. The pre-training data is the ImageNet 1K training set. All self-supervised methods are evaluated by end-to-end fine-tuning. Masked autoencoder can scale up easily and has shown steady improvement from bigger model. Also, they improve over the state of arts, but a non-trivial margin in the highly competitive benchmark of ImageNet 1K. Finally, they evaluate transfer learning in downstream tasks using the pre-trained models. For object detection, they fine-tune masked RCNN end-to-end on COCO dataset. Compared the supervised pre-training model, MAE performs better under all configurations. Also, in segmentation task, pre-training model significantly improve result over supervised pre-training. Okay, thank you for listening.
Okay, thank you very much. There was one question by Q. Why take MSA only on the mask patches? Please answer that.
잠시만요. 이게 논문에서 그냥 되게 짧게 MSE를 쓴다고, 쌍국어로 말해도 되나요? 네네. 그래서 제가 논문에서는 그냥 그 마스크드 패치에만 쓰는 이유가 자세히 나와 있진 않고 그냥 BERT랑 같은 방식을 사용한다고만 나와 있어서 제 생각에는 BERT에서 그렇게 마스크에만 MSE를 했을 때도 성능이 잘 나왔기 때문에 그렇게 한 게 아닐까라고 생각을 합니다. 그리고 다 로스를 주는 것보다 마스크드에만 패치를 줬을 때만 로스를 줬을 때가 더 약간 컴퓨테이셔널도 낮을 거잖아요. 근데 그러한 방법이 BERT에서 잘 된다는 거를 입증을 했기 때문에 이 논문에서 그렇게 한 것이 아닐까라고 생각을 하였습니다.
Thank you. There was one
네.
more question. It's very interesting question, right? So about position embedding for the only visible token. So please, yeah.
사실 이 부분에 대해서도 그 논문에서 그 포지셔닝 에 대한 딱히 그런 어밸리에이션 스터디가 나와 있진 않은데 일단은 이 논문에서는 그 아예 패치가 그 인코더 전에 포지셔널 인베딩을 할 때 아예 그 마스킹을 하기 전에 포지셔널 인베딩을 한번 하고 그리고 디코더에 넣기 전에 포지셔널 인베딩을 한번 그렇게 하잖아요. 근데
네, 그러면 이제
네.
마스크가 그러니까 인코더에 들어가는 것들이 이제 잘려서 들어가는 건데 그 잘려서 들어가는 거에 어떻게 보면은 약간 위치적으로 어디가 어느 포지션인지가 어느 정도는 이제 들어가게 되는 거잖아요.
그 인코더에 들어갈 때요?
네네, 그 위에 그림 보면서 얘기를 하면 좋을 것 같은데 이제 원래대로 이제 이 그림에서만 보면은 그냥 사진들만 스택을 해서 이제 들어가는 식인데 포지셔널 엠베딩까지 더해가지고 마스킹을 해가지고 넣는 거니까 사실은 어느 정도 저 패치의 위치들이 정보가 같이 들어가게 되는 거잖아요. 그러면
네.
어디가 마스크가 되어 있는지에 대한 정보가 간접적으로 좀 들어간다고도 볼 수 있을 것 같은데 이제 그런 것들이 성능에 영향을 줄지가 좀 궁금했거든요. 그래서.
근데 어느 정도 줄 수 있을 것 같다고 생각은 드는데 사실은 이렇게 패치로 자르고 마스킹을 하기 전에 일단 포지셔널 임베딩을 한번 하잖아요.
네네네.
그리고 얘를 완전히 랜덤으로 샘플링을 시킨단 말이에요. 근데 그러면서 어느 정도 포지션에 대한 정보가 손상이 좀 이렇게 손실이 생기지 않을까요? 그러고
네,
나서
그럴 수 있을 것 같아요.
네, 그래서 제 생각에 디코더 전에 포지셔널 임베딩을 한 번 더 해서 얘네 위치를 찾아주는 게 이렇게 랜덤 샘플링 하는 과정에서 그러한 정보가 좀 손실이 되니까 그거를 그 전에 한 번 더 해줌으로써 잡아준다고 저는 생각을 했습니다.
네, 감사합니다.
네. 혹시 더 질문 없으면은 코드 리뷰로 넘어가도 될까요?
네, 그렇게 합시다.
어,
아우,
제가 네, 사실 코드 리뷰를 한글로만 준비를 해서 죄송합니다.
feel very sorry because she prepared the code review in maybe Korean. So yeah, if you have a question, please let me know or let her know. So okay,
네.
Jie, please start.
네, 화면 보이시나요? 일단은 코드가 깃허브에도 제가 그 깃허브에도 따로 정리를 해놨는데 VS 코드로 보여드리는 게 더 편해서 일단 이렇게 하도록 하겠습니다. 사실 이 코드 같은 경우는 그 페이스북 AI 리서치에서 올라온 공식 코드를 가지고 왔고요. 그 들어가기 앞서서 이 코드 말고 그 잠깐 보여드리자면 잠시만요. 이 루시 드레인이라는 분께서 MA 코드를 그 96줄로만 해서 정리해서 올려놓으신 코드가 또 깃허브에 있어요. 그래서 혹시 나중에 MA 코드를 사용해서 어떤 다른 어플리케이션을 하고 싶은 분들은 그 페이스북 공식 코드도 좋지만 이렇게 간단히 정리된 코드도 있으니까 이것도 보시면 좋을 것 같습니다. 네. 네, 일단은 저는 공식 코드로 준비를 했기 때문에 이걸 먼저 보여드리자면 코드는 이렇게 보면은 파인 튜닝 하는 코드, 프리트레이닝 하는 코드, 그리고 그 리니어 프로그래밍에 대한 코드가 나눠져 있는데 저는 그중에서 프리트레인에 대한 코드가 가장 중요하다 생각을 했기 때문에 이 코드를 중점적으로 보여드리려고 합니다. 먼저 다양한 어그먼트들이 나와 있고 사실 이것도 그 코드가 굉장히 간단해요. 먼저 한 줄 한 줄 좀 설명을 드리면 똑같이 그 디스트리뷰트들을 이 코드 같은 경우에서도 멀티 GPU를 쓰기 때문에 아까 그 심시장 설명하셨던 분께서 하셨던 말처럼 아무래도 클래시피케이션 태스크이다 보니까 되게 그 배치를 많이 먹잖아요. 그래서 이 태스크도 이 코드도 디스트리뷰트드 DDP를 사용할 수 있도록 이 부분들 코드가 짜져져 있고요. 그래서 일단은 먼저 처음에는 그 아주 간단한 어그멘테이션을 먹이는 것을 볼 수 있는데 그냥 크롭이랑 호리전탈 플립 그리고 노멀라이즈 정도의 그 어그멘테이션을 하는 것을 볼 수 있고요. 그리고 이 부분은 제가 설명했던 것처럼 그 디스트리뷰티드를 위해서 다양한 것들을 정의를 하고 있고 그리고 데이터 로더를 하게 됩니다. 또 이 모델 같은 경우는 이 모델스 MA라고 써있는 코드에서 불러오는 것을 볼 수 있는데 이 부분에 그 랜덤 샘플링 그리고 인코더, 디코더와 같이 모든 스트럭처들이 다 그 정의가 되어 있는데 이 부분은 나중에 설명을 드리도록 하겠습니다. 그래서 이렇게 불러온 모델을 활용을 하고 또 이제 러닝 레이트도 조절을 하고 또 여기 또 디스트리뷰트들을 통해서 데이터 파라렐을 할 수 있게 정의를 해주고 있고 또 옵티마이제이션 같은 경우는 아담을 사용하는 것을 볼 수 있습니다. 그래서 그 다음에 이제 이 불러온 모델을 가지고 이제 트레이닝을 시키게 되는데 여기 보면은 이 트레이닝 같은 경우도 이 train1 epoch이라고 하는 함수로 정의되어 있는데 이거는 또 engine pretrained라는 파일에 들어있고 여기서 이제 로스 같은 게 정의되어 있고요. 이것도 이후에 다시 한번 설명을 드리도록 하겠습니다. 그래서 이 main.py 코드 같은 경우는 이런 식으로 데이터를 로드하고 모델을 불러오고 그리고 트레이닝하는 과정에 대해서 설명이 되어 있고 이제 본격적으로 그 MA가 어떻게 되어 있는지 모델 구조를 좀 보여드리자면 일단 어그멘트를 보시면 가장 그 모델 디폴트로 가져오는 모델은 이 MAVIT 라지 패치 16이라는 거를 불러오게 되어 있고 또 레이시오도 아까 제가 설명해드렸던 것 같이 0.75가 가장 옵티멀이라고 해요. 그래서 이 0.75로 디폴트를 불러오는 것을 볼 수 있고요. 그래서 이 모델 VIT 라지 패치 16 이거가 디폴트이고 이 디폴트 같은 경우는 이 마스크트 오토인코더 VIT에서 다음과 같은 사이즈와 디멘션을 가지고 불러오는 것을 이 밑에서 확인할 수 있고요. 그리고 이제 마스크트 오토인코더 VIT에 대해서 자세히 여기 나와 있는데 사실 굉장히 간단한 게 결국은 VIT, 인코더랑 디코더가 다 VIT랑 똑같이 생겼잖아요. 그래서 코드 자체도 사실 VIT랑 굉장히 유사하다고 볼 수 있습니다. 먼저 패치 임베딩을 해주고 이 패치 임베딩 같은 경우랑 이 블럭 같은 경우는 그 TIMM의 그 VIT가 함수가 정의되어 있어서 거기서 불러오고 있고요. 그래서 패치 임베딩을 하고 클래스 토큰과 포지셔널 임베딩을 정의를 하는 것을 볼 수 있고 또 블럭 같은 경우는 트랜스포머 블록을 뎁스의 크기만큼 쌓고 있는 것을 볼 수 있습니다. 또한 디코더도 그 인코더랑 동일한데 여기서 또 다른 점은 그 마스크 토큰을 따로 정의를 줍니다. 왜냐면은 인코더에서는 마스크 토큰 부분을 안 넣고 그 안 지워진 부분만 넣지만 이 디코더 때는 마스크 토큰 부분도 같이 더해져서 넣어야 되기 때문에 여기서 따로 그 1, 1, 그리고 임베딩 디멘션 크기의 매트릭스로 통해서 마스크 토큰을 정의하고 있고요. 또 포지셔널 임베딩 디코더는 똑같이 아까 인코더랑 똑같이 VIT에서 사용했던 구조로 이루어져 있는 것을 확인할 수 있습니다. 그리고 이제 이니셜라이즈들을 하고 있고 그리고 이제 트랜스포머에 들어가기 전에 당연히 패치 파일을 해줘야 하기 때문에 이 패치 파일 함수들이 정의되어 있고요. 그리고 이후에 이제 언패치파이 하고 다시 이미지를 생성하기 위해서 언패치파이도 정의되어 있는데 사실 제가 되게 간단히 설명하고 넘어간 이유가 이게 다 결국은 VIT랑 동일하거든요. 그래서 모두 아실 거라 생각을 해서 이런 부분들은 빨리 넘어가도록 하겠습니다. 그리고 이제 이 논문에서 가장 핵심이 저는 랜덤 마스킹을 어떻게 하는지라고 생각을 하는데 일단은 아까 마스킹 레이시오를 0.75로 저희가 정의를 했잖아요. 그래서 이제 그 부분을 제외한 그러니까 1빼기 마스킹 레이시오만큼을 이제 킵을 해주고 있고요. 이 벡터를 이 len 킵이라는 벡터를 통해서 그리고 먼저 노이즈를 정의를 해줍니다. 이 노이즈 같은 경우는 이 이미지의 그 0번째 쉐입이랑 1번 그러니까 두 번째 이를 가져와서 n 곱하기 l 짜리에 그 랜덤하게 생긴 매트릭스를 노이즈로 정의를 하고 있고요. 이제 얘네를 이 노이즈를 사용을 해서 랜덤으로 이제 어느 부분을 마스킹 할지를 랜덤으로 정해주게 되는데 이 부분이 이 IDX 셔플이라는 부분입니다. 그 다들 좀 아시겠지만 토치, 얼그, 솔트가 어떤 역할을 하는지 약간 간단히 설명을 드리면 이 노이즈라는 텐서를 받아와서 그 안에는 다양한 이제 벡터들로 다양한 숫자들로 이루어져 있을 거잖아요. 근데 걔네를 오름차순으로 정렬을 해서 인덱스를 반환하는 친구입니다. 그래서 노이즈가 랜덤으로 정의가 되어 있기 때문에 얘네를 다시 오름차순으로 정렬을 해도 결국 랜덤이잖아요. 그래서 이 IDX 셔플은 랜덤으로 그 매트릭을 셔플한다고 보실 수 있고요. 근데 그렇게 해서 오름차순으로 정렬된 거를 다시 한번 오름차순으로 정렬을 하기 때문에 결국은 이 셔플되었던 매트릭을 다시 리스토어, 원상복귀하는 함수가 이 IDS 리스토어입니다. 이 함수를 여기서 따로 정의한 이유가 그 인코더에서 나온 후에 다시 디코더에 넣기 전에는 다시 원래 그 로케이션대로 정의를 해줘야 되잖아요. 그때 이 IDS 리스토어이라는 그 벡터 이 벡터가 사용되게 됩니다. 네, 그리고 그래서 이렇게 이제 IDS 셔플에서 이 아까 저희가 len-keep이라고 정의함으로써 그 어느 정도 보존할 것인지를 정해줬잖아요. 그래서 딱 그 앞에서부터 그 부분까지만 잘라서 그 IDS keep라는 그 함수의 보존을 하게 되고 이제 그 마스크드 x가 그 보존된 부분에 인덱스에 해당하는 값들만 남겨둔 그런 x 이미지를 얻게 됩니다. 이제 그래서 이 x 이미지를 인코더에 넣어줘서 학습을 시키게 되겠죠. 그리고 마스크 같은 경우는 이 앞에 부분을 다 0으로, 그러니까 우리가 이 앞에 부분을 보존하기로 했고 나머지는 보존 안 하기로 했잖아요. 그래서 이 마스크가 이 앞에 부분, 그러니까 그 보존하기로 했던 부분을 다 0으로 두고 나머지만 둔 그 매트릭이 되는데, 그래서 이거를 앞에 부분이 이제 다 0이 되고 이 나머지 부분들이 결국 마스크니까, 네, 아무튼 그렇게 마스크를 정의를 하게 됩니다. 그러고 나서 마스크 같은 경우에는 아까 셔플이 다 되었는데 이 상태로 디코더에 넣어줄 수 없으니까 다시 원상복귀를 인덱스를 IDS 리스토어라고 아까 정했던 원상복귀 시켜주는 인덱스를 활용을 해서 그 정렬을 하는 것을 볼 수 있습니다. 그래서 이거를 통해서 마스크드 된 부분들이 사라진 이제 이미지랑 그리고 마스크 부분 그리고 어떻게 그러니까 다시 원상복귀 시키는 인덱스 이 세 개를 리턴하는 것을 볼 수 있습니다. 그리고 이제 포워드 부분에 들어가면 일단 이것도 사실 VIT랑 동일하게 패치 인베딩을 시키고 그리고 클래시피케이션 토큰 빼고 포지셔널 인베딩을 시키고 그리고 이제 이 이미지랑 그리고 아까 정했던 마스크 레이시오를 넣어줌으로써 그 이미지 그리고 마스크 그리고 IDS 리스토어를 그 반환하게 되고요. 이제 그래서 이 X를 인코더의 블럭에 넣어주는 것을 볼 수 있습니다. 이제 이렇게 받은 X 이미지를 가지고 이제 디코더에 넣어주게 되는데요. 근데 이 디코더에 넣어주기 전에는 아까 말했던 것처럼 마스크를 붙여줘야겠죠. 그래서 이 마스크 토큰이라는 것을 아까 그 맨 처음에 그 디코더 함수에서 정의했던 마스크 토큰을 가지고 와서 이 IDS 리스토어의 그 첫 번째 렌, 그러니까 IDS 리스토어의 렌에서 이 X 부분을 뺀 거. 그러니까 이거가 전체 이미지고 이거가 그 마스크 된 거 뺀 애들이잖아요. 그래서 그걸 두 개를 뺀 거니까 결국은 그 마스크가 된 애들, 마스크가 되어 있는 패치의 크기만큼을 반복시켜 줌으로써 마스크 토큰을 정의하게 됩니다. 그리고 이제 이 마스크 토큰을 이제 이 아까 인코더를 거쳐서 나왔던 X에 붙여줌으로써 디코더에 넣어줄 이미지를 생성하게 됩니다. 그리고 이제 똑같이 포지션을 인베딩 해주고 디코더 블럭에 넣어주는 모습을 볼 수 있습니다. 이렇게까지가 아까 그 페이퍼에 나와 있는 마스크 오토 인코더의 전체 아키텍처 구조이고요. 로스 같은 경우는 아까 설명해 드렸던 것처럼 MSE 로스만 사용하는 것을 볼 수 있습니다. 여기 나와 있죠. 그리고 또 마스크에만 아까 마스크의 부분에 그러니까 리무브드 된 패치 부분, 그러니까 마스크 부분에만 로스를 준다고 했잖아요. 그래서 이것도 이렇게 정의되어 있는 것을 확인하실 수 있습니다. 그래서 전체 아키텍처는 이렇게 이루어져 있습니다. 네. 네. 혹시 여기까지 질문 있으신가요? 네, 이렇게까지가 이제 마스크 오토 인코더의 전체 코드였고요. 추가적으로 제가 그 마스크 오토 인코더 공식 그 깃허브에 들어가면은 비주얼라이즈가 되는 데모 그 콜앱 파일을 올려 두었더라고요. 그래서 그 코드를 잠시 보여드리려고 합니다. 네, 그래서 이 비주얼라이제이션을 하는 데모 코드인데요. 일단 시간이 걸려서 제가 더 눌러놨는데 먼저 여기서 이미지를 이제 보여주는 쇼 이미지 함수를 정의를 하고 그 아까 그 프리트레인드된 코드를 활용을 해서 돌렸던 그 체크 포인트를 불러오는 프리페어 모델 함수가 있고요. 그리고 이제 run1 이미지가 이미지 한 장에 대해서 프리트레인드된 모델을 적용해서 이제 마스크랑 그러니까 제너레이티드 이미지를 얻어내는 run1 이미지 함수를 정의하고 있습니다. 이거를 간단히 설명을 드리면 먼저 이미지를 텐서로 바꿔주고 스키즈하고 퍼미테이션을 해주고요. 그리고 이제 이거를 아까 보여드렸던 그 아키텍처 모델에 넣어주면은 로스랑 그리고 Y 그 리컨된 이미지 그리고 마스크 3개를 얻어낼 수 있습니다. 그리고 이제 이 Y를 언패치 파일을 하고 다시 퍼미테이트를 하면은 이미지가 생성이 되겠죠. 또 마스크 같은 경우는 언스키즈하고 똑같이 언패치 파이하고 또 퍼미테이트 하면 또 이것도 마스크에 대한 이미지가 생성이 되는데 이제 이거를 이래서 이 이미지 마스크드라는 부분이 그 이미지 1에서 마스크 부분을 뺀 나머지의 부분들에는 X를 넣어주고 마스크 부분에서는 리컨된 이미지, 그러니까 생성했던 이미지를 넣어줘야 되잖아요. 그래서 원본 이미지는 마스크 부분 빼고는 원본 이미지를 넣어주고 마스크 부분에는 리컨스트럭트된 이미지를 넣어주는 모습을 확인할 수 있습니다. 그래서 이렇게 정의된 함수를 활용해서 이미 생성된 이미지를 보여드리면 이렇게 여우 이미지를 여기서 불러와서 이거를 아까 설정했던 모델에 넣어주면은 이렇게 오리지널 이미지가 있고 이렇게 0.75%만큼 마스크된 이미지가 나오고 이제 이 부분들을 제외하고 이 마스크가 되지 않은 부분들, 마스크된 부분들을 생성했던 이미지가 나타나는 것을 확인할 수 있습니다. 그리고 추가로 그 간 로스를 더 추가를 하면은 더 리얼리스틱한 이미지를 얻을 수 있다고 하는데요. 그렇게 했을 때 아까 이미지에서는 약간 이렇게 패치 부분들이 남아 있는데 이런 식으로 조금 더 리얼리스틱한 이미지를 보여주는 것도 비주얼라이즈 하고 있습니다. 네, 여기까지 마스크드 오토인코더 코드 리뷰였습니다.
Okay, question. 그 재학생 제가 좀 퀘스천 있는데 그 방금 마지막 거를 전 처음 봤는데 저도 마지막
네.
보여줄래요? 간로스 붙인 거. 요게 그 오토인코딩 학습할 때 간로스를 붙일 때 그 간은 그냥 모든 픽셀에 다 붙는 거죠? 마스킹만 붙는 게 아니라.
사실 이 부분에 대한 코드가 딱히 없어서 제가 제대로 못 봤는데 제 생각에는 패치마다 붙는 게 아닐까 싶습니다.
패치마다?
그냥 간 로스 평소에 붙는 것처럼 이
어.
이미지 전체에 대해서 간 로스를
이미지
하는
레벨
게.
그쵸?
네네,
아,
이미지
네네.
레벨이죠. 네.
그러니까 그 제 생각에는 아까 저게 간로스를 붙여서 리컨이 잘 되는 것도 어느 정도 있을 거긴 한데 사실 저 위에 있는 위에 있는 네트워크는 저 비저블한 부분에 안 붙잖아, 로스가 아무것도.
네.
그럼 딱 그럼 보면 비저블한 부분만 이렇게 뭉택이 지는 것 같은데 이렇게. 그러니까 저런 게 그러니까 저기 로스가 안 붙어서 그랬던 것 같은데 저 비저블한 부분에 그래서 저게 간로스는 어쨌든 비저블한 부분까지 다 붙으니까 저렇게 스무드하게 잘 나오는 것 같긴 한데 꼭 궁금한 게 그럼 저렇게 간로스가 리컨이 잘 되도록 해주는 거 플러스 저 레프렌테이션 자체도 더 잘 배워진다고 하나요?
사실 그러니까 간 로스에 대한 설명은 어디에도 없고 정말 이 비주얼라이즈 하나에만
어,
있거든요. 근데 네, 뭔가 레프레젠테이션이 잘 되는지는 저도 잘 모르겠는데 일단은 그냥 이 네트워크, 이 아키텍처, 그러니까 이 보통은 이 MA 자체가 결국은 프리트레인드 된고 나중에 이제 트랜스퍼 러닝이나 리프레젠테이션 러닝으로 파인 튜닝 하려는 용도로 보통 사용을 하는데 그게 아니라 간 로스까지 붙이면은 리컨스트럭션도 되게 이렇게 리얼리스틱한 걸 잘 한다라는 걸 약간 보여주려는 용도지 않았을까라고 저는 생각을 합니다.
이게 왜냐하면 사실 우리가 뭐 이번 시간에 얘기했던 그냥 사실 우리가 얘기했던 셉션al 러너들은 다 디스크리미네이티브 모델들이고 이론적으로 제너레이티브 모델들의 사실 피처 벡터들도 원래는 그러니까 제너레이티브 모델에서의 그 VA의 피처 벡터 원래는 사실 슈퍼바이즈 레퍼런트로 배워지는 거잖아요. 근데 그게 어느 정도 잘 레퍼런트 한다고는 알려져 있거든요. 근데 그게 기존의 컨트라스티브 러닝 애들보다 워낙 안 나오니까 사실 못 쳤던 감이 있긴 한데 사실 요게 정말로 간을 같이 붙여서 마스킹 오토인코더라는 요 프레임워크에다가 간을 붙여서 레퍼런트 더 잘 배워줄 수 있다면은 뭔가 그 제너레이티브 모델과 디스크리미네이티브 모델로 둘 다를 이용해서 배워지는 뭔가 효과도 있을 것 같고 뭐 엄청 중요한 메시지일 것 같은데 모르겠네요. 이게 논문에서 못 본 것 같아가지고 네. 한번 고민해보면 좋을 것 같습니다. 네, 알겠습니다.
네.
네, 오케이. 이렇게 마무리하고 right. And thank you. And next paper is PIT. Chuyeon, please stay tuned. Let's start. Let's first present the PIT first because we discussed PIT in the lecture. And the next paper is PEIT, BERT pre-training of the image transformer by Kyusung. This is just the paper review.
들리시나요?
네, 들립니다.
네. Hello, my name is Kyung Lee, and I'm going to present BEIT, BERT pre-training of image transformers. OpenAI's image GPT proposed the pixel prediction task for pre-training, and this paper presents the more generalized concept of masked image token modeling. This paper was released in June 2021, and after this, the masked image modeling papers such as SimMeme, MAE, and iBot are released. First, the authors define the problem and objective like this: to solve the transformers data hungry issue by adapting self-supervised pre-training methods. Previous attempts to adapt VIT for self-supervised pre-training ideas have included Moco version 3 and MOBY and Dino, and many other methods. In whole machine learning fields, mask modeling seems to be the most general idea of self-training or pretext task. So the main motivation and the main question of this research is how can masked language modeling (MLM) can be applied to image domains. The challenge of masked image modeling is how to predict the image pixel or patch from the transformer's output, because image does not have an explicit vocabulary. So there are some ways to resolve this problem, which is regarding the task as a regression problem. So it can predict the raw pixels of masked patches. But according to DALI and Pixel CNN++ paper, which object to image generation from OpenAI, it says that pixel level recovery tasks like Pixel CNN tends to learn the shorter range dependencies and high frequency details. So this pre-training method make the model waste modeling capacities and hard to capture the semantic information. Therefore, they try to overcome these issues for pre-training of vision transformers. This is the proposed overall architecture of BEIT. It has two stages to training. First, it acquires visual tokens by discrete variation autoencoder VA tokenizer. Second, like general vision transformer architecture, it patchifies the image and embedding and replaces some tokens to learnable mask tokens. In this paper, the mask probability is 40%, and passes these tokens to the transform models. First, visual tokens parts to train discrete way in unsupervised way. It trains the reconstruction from the visual tokens, which is in the codebook or vocabulary. Following the DALI paper, the vocabulary size is 8,196. In DALI, it tokenized to size of 32 by 32, so the number of visual tokens is 32 by 32. 32 by 32. So the number of token is 1024. And it is the 1/4 of the image input size, 256. They use some image size modification to match the number of vision transformers token and the number of token of DALI tokenizer. So the input size of DALI tokenizer in BEIT is half of the input size of vision transformer. So the tokenizer input is 112 by 112. Next, the second stage of BEIT is to provide the image to general vision transformer by patchifying the image. It masks some image patches by probability of 40, and the paper said it blockwise masking. So the masked image patch embedding is turned into a learnable mask token, similar to class token. Finally, it merges two stages by pre-training the mask token output from the transformer encoder, and its ground truth is tokenized result from DALI tokenizer. Its token predictor is simple softmax classifier, and it classifies the masked token to some token which is in vocabulary. And it maximizes the log likelihood of correct visual tokens, and it is simply implemented by cross-entropy loss between softmax classifier output and the visual token labels. For experiments, it achieved the state-of-the-art result at image classification on ImageNet 1K without any pre-training on our other dataset. It outperforms any other self-supervised learning methods, and also its performance exceeds the supervised pre-training method with ImageNet 22 kilo. But there may be some concerns about the unfair comparison, because someone can say that it just learns the knowledge from DALI pre-training, which is the reconstruction training of discrete VAE. So in the supplementary material, they also conducted the experiment of re-implementation of deep VAE and pre-trained it pre-train it at only ImageNet 1K, and they found that the performance only dropped for 0.16% points, and the result is in appendix. And the difference with the main table is the training epoch. So this result is just 300 epoch training result, and the main table result is 800 training result. And other downstream tasks such as semantic segmentation, they have very good performance at this task. Thank you for listening to my presentation.
Thank you very much. Question. Question for the IT? No? Okay, thank you again. Let's move to the last paper. End-to-end learning of the visual representation from uncreated instructional video by Juyeon, which is going to be paper plus code review. Okay, Juyeon, let's start.
화면 잘 보이시나요?
네, 잘 보입니다.
아, 네. 저 시작하겠습니다. Hi, I'm Juyeon, and I'm a master's student in the Machine Learning and Vision Lab. Today I'm going to represent the CVPR paper, End-to-End Learning of Visual Representations from Uncurated Instructional Videos. This paper focuses on the representation learning via self-supervision with multimodal data. Multimodality here is about image modality, which is from video clips, and text modality from the captions. I'll explain in detail about the dataset soon, but to briefly mention, the videos and the captions have pretty much weak correlations, and they are temporally loosely aligned. Here, the gray sphere is the representation space, and the red dots are the video embeddings, and the green ones are the caption embeddings. What we want to do here in this learning scenario is that we want the videos and the captions with similar semantic meanings to be mapped closely on the space. And when they're semantically less related, then we want those embeddings to be far apart. So this is like one particular example. It is a video about making a paper doghouse, and the video clips with paper doghouse and the caption with the word doghouse here are closely mapped together in this embedding space, while the clip with only a paper glue and scissor and tape and the caption with no words about doghouse are very far apart. So one of the main limitations of representation learning with vision and language data is that it requires manually annotating large amount of visual data. Especially for videos, annotation is even more challenging. There are ambiguities of choosing the right vocabulary of actions and annotating the intervals between the actions. To tackle this problem, recent work has proposed a way to use narrated videos that are already available at scale on the web. Especially what this paper focused on is the How to 100 Million dataset. It contains 136 million video clips from 1.22 million narrated, uncurated YouTube videos. And there are also associated narrations created using the automatic speech recognition. This dataset was automatically collected by querying YouTube videos for instructional videos. So as the name has the word how to, so I think the authors, the dataset, the people who made this dataset queried using the word how to do something. So the videos are mostly about someone orally explaining how to perform some kind of human complex activity, like how to cook something or how to repair a car or something like that. However, this How to 100 Million dataset also has some problems. As a matter of fact, these videos are not made for machine learning or deep learning algorithms. They are just YouTube videos made by the creators for maximizing the number of views. This means that the supervision in the narration is only weak and noisy. So one typical noise is the weak alignment or even misalignment between the video and the language. As you can see, this is a figure from the paper. This is a video clip. The upper part is the video clip, and these are the corresponding narrations. They actually, well, ideally they should be aligned like this, but as you can see the arrows, they're not aligned or like even crossly aligned. This is because people might talk about something before actually doing it, or they might also don't talk about it because it is clear enough visually. To address the problem of visually misaligned narrations from the videos, this paper makes a set of multiple positive candidate pairs that happen close in time. To explain it in detail, let's move on to the objective. They named it MIL and CE because this method inherits from MIL and NC. MIL stands for multiple instance learning, and NC is noise contrastive learning. The loss basically has a form of contrastive learning so that there are positive samples. I made this blue rectangle, and there are negative samples here. And we want to discriminate between data from the true joint distribution and some artificial noise data or the negatives. And we can estimate the parameters of our model by maximizing this objective. The authors evaluated the representations with 4 downstream tests as follows: action recognition, text-to-video retrieval, action step localization, and action segmentation. They used the learned representations and checked whether they are rich and appropriate for many other video tasks. The tables show the learned representations are competitive with other self-supervised counterparts, as well as some fully supervised baselines. This is the end of my presentation, and thank you. Are there any questions about the paper?
Maybe not. Okay, so thank you very much, and let's move to the code review.
So I uploaded the GitHub link on the presentation Excel file, but I'll do the code review on this VS Code. So the main file is this main distributed type, and there are some evaluation files and video loaders called HMDB loader, MSRVTT loader. They are just the name of the data sets for the downstream task you could as well. This video loader is the main loader for the how to 100 million dataset training loader. So I'll start with this main distributed type. So as the other presenters mentioned, this also has the form of this kind of DDP part here, like multi-processing distributed here. So the main pie also has the name called here distributed. The main part is here called the function called train, and this made this train one batch function. So this is the main training code. So first, this function gets video and text data like this. It is gathered using the loader and handed to this function. So they make each embeddings using the model here. So they make the video embedding and the text embedding. And then using these embeddings, they calculate the loss using this loss function. And then it is pretty simple. They just prop and train, and this is the end of the train one batch function. So this is the loss function. It is actually the same as this objective. It is just the same as this local part and plus the minus at the front. So this the fx from the objective function is the video embedding here, and the gy from the objective function is the text embedding here. So they the x becomes the dot product of the two embeddings like this. And I think they wrote numerator as denominator here, and this is the denominator of the objective function. So in the objective, it was a division actually, but it becomes subtraction in log. So they returned denominator minus numerator. So numerator is the positive pair part. So the positive candidate pairs becomes the numerator. So they multiplied identity matrix so they can get the diagonal positive candidate pairs only, and the denominator gets the positive and negative pairs, which is the whole pairs. So they just got all the positive and negative pairs. So this is the loss function structure. They are just directly implemented from the objective. And then the video loader code is actually the same as the structure is also the same as other video dataset loaders. So I'm just going to use this how to 100 million loader. There are a lot of other functions, but the key function is this get item. So this get item function gets each video and the corresponding caption using the index, and the internal function called get text and get video are used. So I actually got some example JSON file for caption. So this is the caption data. So this is a JSON file with this. These are all the caption text, and there are the corresponding start seconds and end seconds. So this loader gets the text here using the caption JSON file, and with using the find nearest candidates, this function gets the near candidates for the positive pairs, and this words are returned, and these words have the positive candidate caption pairs captions for one video clip. And this is one example of evaluation code. I'm going to explain using the MSRVTT. It is for the retrieval task, and it is also very same as the one mentioned by the clip zero shot from the professor's lecture. It is also the zero shot retrieval task, and so it also gets the text and video data, and using the embeddings, using the model, so we get each embeddings, and the embeddings are fetched to the compute matrix using the dot product. So the similarities are calculated and the metrics are computed. So this is the end of my code review. And are there any questions? Oh.
Thank you very much, Kashan. Okay, I have one question. Do you know how many GPUs to train such kind of large scale? I mean, to train the network on 100 million video scale data set. How many GPUs are used?
The authors used TPUs actually. So they mentioned cloud TPUs version 3, but they they used 4 TPUs.
Oh,
No, 4 TPUs. They used 4 TPUs for evaluation studies, and they used 60 for cloud TPUs for 400K steps.
okay, awesome. Right. So there was another paper question. Application of the paper used yeah. The question is why this paper focused on how to video, instruction video.
I think they wanted to use the supervision by the narrations, because how to video usually has a lot of verbal explanations about the actions. So I think they used the how to videos.
Okay. Any other question? No? Right. Thank you, Juyeon. Okay, so it was thank you. Yes, so it was the last paper, and this is end of the self-supervised laboratory learning part. Yeah, that's it. So as you know, we will have a midterm exam next week, same time, right? So we will cover object detection, segmentation, generative model, and self-supervised laboratory learning. Today's topic, right? And yeah, any other question for our midterm exam? No? Right. Let's finish today. And thank you very much. And see you next week in person. 자, 여러분 오늘 여기까지 하고요. 너무 고생했고요. 우리 이제 다음 주에 같은 시간, 오늘 목요일 같은 시간에 우리 중간고사를 보도록 합시다. 알겠죠? 너무 고생했고요. 우리 다음 주에 보도록 합시다.